Here's Amperes Law in its simplest form. It says that the line integral of B dot dl around any closed loop equals mu naught times the current that passes through it. So if I've got this simple circuit here, I've got current flowing along this wire. If I draw a loop and I calculate B at every point around that loop and do B dot dl, so those need to point in the same direction, integrate all the way around, I'll get mu naught times the current that flows through there. But what if we have, say, a capacitor in our circuit that's being charged up? Well, there's no current that flows across the capacitor. There's a vacuum in between the plates, but we'll still have magnetic field there because we have a changing electric field inside that capacitor. We call that displacement current. It's not real current. It's a changing electric field that gives us an updated or more advanced version of Amperes Law that is all of this combined. Okay, so changing electric fields create magnetic fields. Changing magnetic fields reinforce and create new changing electric fields. So if here on the z-axis I've got some charge oscillating back and forth, that accelerating charge will create this changing electric field, which then creates this changing magnetic field, and we get what we call an electromagnetic wave, otherwise known as light. So our simplest case here is if we have our charge oscillating sinusoidally, like a simple harmonic oscillator, then E would go like sine, B would go like sine. Of course, these have different units. Putting them on the same coordinate system is just to help you visually. This guy has units of newtons per coulomb. This guy has units of Tesla, completely different units, but the directions are here. B is always perpendicular to E, and the wave propagates in the direction perpendicular to both of them and follows the right-hand rule. That's called the pointing vector. We'll get to that in a minute. Okay, now electromagnetic waves are waves, so they need to satisfy something called the wave equation, which if we plug our E and our B into, imply this, that the speed of propagation is 1 over epsilon naught mu naught. So I've got this wave. I'm not talking how fast it's oscillating up and down. That's called our frequency or our period. So the number of times it oscillates per second would be the frequency. Period is how long it takes to do one oscillation. That's not what we're talking about here. We're talking about how fast this energy gets traveled in the x direction. Remember, nothing is physically moving in the x direction. Our charge is back here at the origin. Energy is propagating away from that in the form of a wave that we call light. And that moves at this speed, 1 over epsilon naught mu naught. We have a name for that. The speed at which light moves, we call that the speed of light. Just plugging in our numbers for epsilon naught mu naught, it's about 3 times 10 to the 8th meters per second. And remember, wave speed is frequency times wavelength. So for any kind of light, the frequency in hertz times the wavelength in meters always equals the speed of light. Okay, light can be polarized. So polarization means all of you got a whole bunch of light. Every single individual photon is polarized. But if we have a whole bunch of light shining at us, it may all be oscillating in the same direction. If it's all the E's are going up and down like this, we would say this is up and down or Y polarized. If it's all going left and right, the E fields, we would say that would be Z polarized. This is light coming from the sun is generally unpolarized. It's a mixture of all the different polarization directions. But once it gets through the atmosphere and it bounces off, say, the ground, it typically bounces back up vertically polarized like this. So polarized sunglasses have strips in them that block out light that's polarized, say, in this direction. All that gets through is like this. Since most of it bounces off like this, that's why light looks dimmer through polarized sunglasses, because only the tiny bit that didn't get polarized that looks like this gets through. Okay, we can go further into that if we wanted to with Malice's law, but we're not going to. Okay, so electromagnetic waves we call light. All of this that we see here describes light. So light can be anything from very high frequency, gamma rays, like what created the Incredible Hulk, to very low frequency, what we call radio waves. But this is all light. So when you get in your car and you tune your radio to 101.7, that's 101.7 megahertz. Those are radio waves. Those have wavelengths on the order of kilometers long, but very or relatively high frequency. Here are the giant frequency and tiny wavelengths. The stuff we can pick up with our eyes we call visible light. That's a very, very narrow spectrum of the entire electromagnetic spectrum. This is just what we can see, this tiny little sliver in here. We've evolved to be able to see this because this is what's around us the most. This is what's the most important here on Earth. Some animals have a much broader range. Some animals can see into the ultraviolet and infrared spectrums. Okay. The Poynting vector, named after the physicist Poynting, is this vector that points, P-O-I-N-T-S, in the direction of propagation, and it's E cross B. So go back to our picture of a wave. E is pointing up, so point your fingers up. B is towards your face, so curl towards your face. E cross B, your thumb points along to the right down the x-axis. That's the direction of propagation. The Poynting vector tells you which way the light is shining.